Hello, everyone, and welcome back to HDL for Digital System Design. I'm Dr. Mike Brovchek. We are diving right back into topic two, which has been covering combinational building blocks. So far we've seen that operators can consume and produce hardware of varying sizes. Also talked about briefly different data types that exist. Well, we don't normally operate on individual bits in our systems, right? That wouldn't be very efficient. So we need to talk about how size literals and width matching actually happens, right? When we start talking about larger structures, larger bit widths. So without further ado, let's dive in. All right. So where does this actually live? Well, in most corporate spaces, you're going to have a set of rules that um, you're going to want to follow. You're going to want to make sure are the case for the things you write. So you might be familiar with the concept of linting when it comes to writing traditional code. In general, linting does not find syntactical issues, right? It actually finds issues that might be related to following specific policies, procedures, or styles that people will want imposed or enforced. So the same thing actually happens when we talk about Verilog or HDLs. That basically there are tools that will look for patterns that, again, are not syntactical issues, but are likely issues in terms of how you've constructed things from a stylistic standpoint that sometimes lead to discovery that you probably have a bug um, that, again, what you've built, while syntactically correct, is probably not going to produce the results that you expect. So commercial tools like Mentor, Verissimo, or Spyglass, or Verilator flag some of these issues. Um, One of the issues that, and again, what we're going to talk about today, is one that deals with explicit width. And it is one of the most common linting rules that exists. And why? Well, because these issues with the size mismatches or assuming that a specific um, thing that you have has a width when it really doesn't, or that it has a width of a different size than you expect happens all the time. Now, unfortunately, Verilog doesn't come with the same set of linting powers behind it, but Verilator, which is another open source tool, does, and so we'll actually leverage that a little bit in this lecture. So again, this is going to build up. We're going to see this throughout the rest of the semester. We'll see it most immediately in our next topic, the ALU, where the result of all of your operations matters deeply. We'll see it again. It'll continue. Topic 4, we'll talk about it. We'll see it when we talk about different mathematical operations. We'll see it when we talk about communication. It shows up everywhere. So really paying attention to the size of your data and when it gets transformed, what is the resultant size will be critical. So um, again, with experience, you'll be able to look through code and recognize mismatches. Um, so if you are thinking from a very traditional programming standpoint, it might be hard to see this. We don't normally have to think about this when we talk about traditional programming. Um, but for sure, when you talk about hardware, we need to really pay attention. And hopefully this lecture exposes you to that. Okay, so biggest gotcha. Just writing 0 or 1. Um, in an HDL like Verilog does not produce the same behavior as writing 0 or 1 in C, right? In C, um, essentially, the compiler figures out the width from the context and also how you've defined your variable. But in general, if you have a variable and then you say equals 0 or equals 1, the 0 or 1 size is essentially implied or implicit from basically the other side of the assignment statement. So that is happening. Now, unfortunately, that is not what happens in Verilog. In Verilog, whatever you type, if you don't specify a size, it defaults to 32 bits. Um, Again, this is not how we normally think of things. So mismatches are truncated or zero extended, depending on which way the mismatch happens, silently. So simulations will pass, synthesis will pass, your waveform will tell you one thing, but it's not actually what will happen necessarily in hardware. Okay, so here's an example of that. Imagine that you define X to be a wire that's 4 bits long, and you set it equal to the number 1111 in binary and add what to it, right? So imagine that you do right here, right-hand side is equal to this. Well, this 1, because you haven't specified otherwise, is a 32-bit number. So the addition is 32 bits, the assignment truncates, and your result ends up actually being 0. By the way, this would be the same if you had, this is a 1-bit number, but doesn't matter. Here we claim that iverilog warns you if you use wall. This is actually only if you have a certain version of iverilog. We will show you how you can still get this answer by using verilator. So the other thing here is you'll notice that being able to see some of these warnings requires turning on all warnings. And a lot of times people don't do this because it produces a lot of extra output. I'm going to tell you that you should consider turning on some of these, especially as you're getting started. Okay, so here is a very quick setup here. Let me try to make this a little bit bigger for you. Um, Okay, what we have here is just format specifiers for different literals. Notice that you can define things in binary. So if you wanted a 4-bit binary number, basically 4, a single quote B for binary, and then your binary number. If you wanted to define 8 bits in hex, 8, again, single quote, H, and then the hex values, for example, FF would give you all ones. This would be equivalent to doing 8 single quote decimal D 255, right? Those result in the same thing. You could also do 8 single quote B 11111111, right? 8 ones there. All of those are equivalent, but the hex representation is preferred in most cases. Let's see, going down the list, you can define 4 bits, 4, and then a single quote, D9, if you wanted to define it as a decimal. 1 bit, so 1 single quote, B0 or 1 could get you a single bit. Same thing, you want a 32-bit number, you tell it 32 bits, single quote, then your specifier, right? So let's say decimal D0. 16, so 16 bits, single quote H, going to be a hex value, A, B, C, D, right? All those happen to be hex values. So in general, width, a single quote, your base, and your value in that base, right? So make sure your value matches the base that you're writing in. So get into the habit of always specifying a width. Use hex for multi-bit constants. That's generally how I do it, unless I'm encoding a specific pattern that, again, means something in binary. I'm going to use binary representation. I use underscores every 8 bits for anything that's over 8 bits wide, just for readability. So you can definitely do that. So down here at the bottom, and I usually separate on every 4, not necessarily every 4 bits, but every 4 characters. So you'll notice here I have a 32-bit number in hex. I basically do H1234 underscore 5678. Again, this is just an example. Clearly, those could be any hex value from 0 to F. 8-bit value here, 8 single quote B, and then what you see here is 1011 underscore 0010. Again, I try to separate on either 4 bits or 4 places, depending on the representation. Okay, so wonder if you can spot the width bugs here. I have two wires, wires A and B. Wire A and B are both 4 bits wide. Wire A is 1010, or the value of 10, and wire B is 0110, or 6 in decimal. So I now have a wire sum, also 4 bits, that's equal to wire A plus wire B's value. Clearly 10 plus 6, I would expect 16. The question is, what do we really get? Next, I have wire doubled, which is a shift on A. So if I shift A to the left, right, 20 doubled essentially, right, should be 20, right? So 10 times 2 should be 20. What do I actually get? So see if you can figure those out. All right, so here's the answer. If you were to do the sum, you're going to get an overflow, right? So if you are going to try to sum up both of these, you're going to get 16. 16 does not fit into 4 bits. Specifically, it is 5 bits and it's 1, 0, 0, 0, 0. So there you go. Can't fit it in, so you're going to get a result of 0 left in the sum, which is probably not what you're expecting. Um, the doubled actually operates the same way. If you were to shift the value of A 1 unit to the left, you would end up with, you would expect 5 bits, and you'd get 1, 0, 1, 0, 0, but that first bit gets truncated, so you're left off with 0, 1, 1, 0, 1, 0, 0, or 4. So your most significant bit has shifted off. Um, so the simulation will work. There'll be no problem with this. It just won't give us the right answers at all. So simple fix here is widening our sum by 1 bit, right? So it was 4 bits, right? 3 down to 0. We need 1 extra bit to store this. If we're doing multiplication, you need twice the number of bits to be able to store potential overflow. Okay, so are you able to predict these? So I've got 4 examples here. I've got a wire x1, which is 4 bits wide, attempting to add 5 plus 12 together. What's going to be the result? What will x1 hold? Same thing, 2. x2 is 5 plus 12, but it has, let's see, it's defined as 5-bit. Go down to example 3. We have an 8-bit wire called x3, which is ff plus 1. What will that be? Notice that there is no description on what 1 is. And then number 4, again, another 8 bits, adding ff plus, being super specific here, 1 represented as an 8-bit number. So what's the result of these? So ultimately, what we get here is, for number 1, we are going to get the value of 1, 17 truncated down to 4 bits. Number 2, well, since we have 5 bits wide, we are going to be able to store that. We're going to get 17. For number 3, our summation here ultimately is going to yield the hex value 0, 0. We're going to roll over. Notice that the literal 1 is 32 bits. That addition is going to happen, but it's still going to get truncated down to 8 bits. We get the same answer for number 4, but we are being specific in terms of what we're adding in. The fix here is to make a 9-bit number on at least the 4th one. The question would be, in order to fix 3, to not have any truncation, assuming that 1 is a 32-bit number, what would we have to do? Okay, so let's take a quick look at a live demo. This is in the lecture examples, week 1, day 2, segment 3, exercise 5. So let's take a quick look here at the terminal. We are already there in the terminal. in that location. Let's take a quick look. Let me make clean real quick, just so that we can see what's going on. We have a makefile in here that allows us to explore the linting process to see those bugs, and then we'll look at the synthesis output and simulation output as well. So let's start off with the make lint. What this is going to do is, you can actually see the command here. It's going to look at verilator lint only, all warnings, and it's going to do this on our very simple file. Let's take a look at it real quick before we move on. So this width bugs has some deliberate bugs in the width of things, right? So what we have inside of here, A, B, big value. A and B are both 4-bit wires. Big is an 8-bit wire. We get some truncated summations, some summation overflows, widen and a narrowed register as well. So bug number one, truncated A plus B plus 1. So taking A plus B, right, 4 bits, adding value 1, which is 32 bits, right, and trying to put it into some truncated, which is also just 4 bits. There's a problem with that, even if we didn't include this one at the end. Bug 2, 5-bit add result added back to a 4-bit register. So some overflow. Basically, we have here one bit plus concatenated with A, so that makes it a 5-bit number. Same thing on B, making this a 5-bit number. Just trying to add both of these together, seeing what happens, so on and so forth. So also trying to set A, which is a 4-bit number, setting it equal to a widened value. So widened is 8 bits. Can we assign widened that is 8 bits to a 4-bit number? What happens there? And bug 4, what happens when we go the other way? What happens when I have something that's big and assign it to something that's smaller? So big here is 8 bits. And what happens when I try to assign it to something that's only 4 bits? All right, so with that, let's do a make lint and see if we get any errors that show up, or warnings, I should say, not errors. So let's do make lint. And what we see here is we do get a handful of warnings, right? We get warnings here that basically say, well, they're basically telling us that we can turn off these warnings if we want, but we are getting essentially operator expects 4 bits on the assign right-hand side, but assigns right-hand side add generates 5 bits. So basically it's saying, hey, the right-hand side of this generates 5, but you have only 4, right? It's expecting 4, you're assigning 5. Here, expects 8 bits, but the assign here generates 4 bits. So basically we're seeing mismatches across the board here. And so these are, again, not going to be syntax errors, and I can prove this by doing a make synth. So let's synthesize this. And what we get is we get synthesizable code, right? It synthesizes no problem. We can make sim, and the sim does show us because we have some logic checks in here that are double checking that, whether or not we have issues. But we can view this, right, and show that it does generate. Let's look at our waveforms here real quick. So what we see here is our ability to, we get fully synthesizable code, right, hardware, and we see that essentially it does work. No problems, right? Had we not viewed the linting result, um, we would not detect any of these issues. So I'm going to shrink this down a little bit here and try to find a good representative space here. Let's see. We were doing A and B and trying to put it into Let's take a look real quick again. Let's look at width bugs.verilog here. And so A and B are two smaller values trying to put it into some truncated. Yeah, so let's look at, I'm going to highlight these A and B. Let's change these to orange. And we were trying to put them into some truncated. I'll make it orange and I will, for convenience, move it right up here. Okay, and let's change these, since these are all pretty small numbers, let's change these to decimal numbers. Okay, so 0 plus, so 15 plus 0, we would have expected this. Oh, there is one other thing, sorry. We're adding 1 to this every time, right? So if we go back here, you'll notice right here, we add 1, right? So 15 plus 0 plus 1 is 16. It does not fit into our truncated space. We get 0, right? 9 plus 9 plus 1 is 19. What do we actually get? We get 3 because that is essentially the overflow that comes back, right? So we're just getting the what remains in the lower 4 bits always, right? If we wanted to solve this, right, we would have to create a larger space for this to go. So let's take a look. Let's do, I think if we look at sum overflow, we'll get close. So sum overflow makes these 5-bit, well, makes each of these 5 bits, it's going to overflow, but we're appending a 0, so it shouldn't be too bad. But let's make sure sum overflow is also 4 bits, so I take that back. So if we want to fix this, right, real quick, let's go and fix this and rerun it. So with bugs verilog, what I'm claiming here is that if we want to fix this overflow, instead of sum truncated being 4 bits, let's make it 1 more bit. And let's rerun this real quick. Let's make sim and make wave. And let me reload this real quick. All right, so reloading the waveform here. What we should see is, oh, did I not? Let's double check here. All right, sum truncated. Still shows up. Oh. Right here. All right, so now that we've changed both of these, and we do a reload, waveform, what we should see here we should see some truncated. Now be careful, this is still in hex, so let's change this back to decimal. And we now see that it works as expected. 15 plus 0 plus 1, right? So remember that this sum in here is a plus b plus 1. A plus b plus 1, which isn't shown here, is 16. 9 plus 9 plus 1, 18 plus 1 is 19. We're now getting the expected answers. So be careful. I mean, I kind of did a little bit of a quick job there in terms of changing the code and reloading on top of a existing GTK waveform. Does cause a little bit of issues in terms of how it renders. Um, but in any case, you can see that our change, now that it's 4 bits, two 4-bit numbers now added to a 5-bit number, we're getting what we expect. Okay, so let's head back here. So ultimately, the point to take away here is that it is entirely possible for you to write syntactically correct code that does not behave as you expect. So it is recommended, if you have access to it, either a commercial tool or Verilator, for you to lint to look at how things are happening behind the scenes. Make sure that you don't have mismatches in terms of what you're doing. Okay, so um, here's the code. If you were to do the stat on the buggy code and a fixed code, it is not that expensive, right? So there's very little reason to not have correct widths. Auto truncation or truncation really rarely makes sense. So uh, it comes at a very low cost. One extra LUT is really all it would cost us to fix from going from an add to this of the same space. So basically adding two 4-bit numbers in a 4-bit resultant versus two 4-bit numbers into a 5-bit resultant. Literally the difference is 1 LUT. So don't undersize a sum or product. Your hardware savings are going to be trivial. Okay. I will say a product, it's not as trivial, right? Because you have a doubling of space. But again, it's rare that you're going to just want the lower half of that result. So ask, if you're going to use a large language model, try to ask it in Verilog, what's the bit width of 1? What about 8D1 or 1B1, right? Doesn't know. Ask it about widths of these 3 literal forms. Predict, what do you think it's going to say? Is it going to tell you that 1 is actually 32 bits and that all of them have the value of 1? If the AI is good, it should get it right. If a model happens to tell you that 1 is 1 bit, it's wrong. Would not recommend using that for Verilog. So it's a quick diagnostic check for you. If an AI says 1 is 1 bit, switch models, don't use it. So the reference behind the scenes here is actually a standard on IEEE standard 1364-2005. Unsized numbers are at least 32 bits. That's why 32D1 and 1 behave identically in most expressions. Right, big takeaways for this one. Unsized literals are 32 bits. They do not get auto-sized. Always, always, always size your literals. So use 4 bits wide. D1 for if that's what you want. Don't just use 1, right? Use 1B1 if you want 1 bit. Always size it to what you need and what you want. Don't make an assumption. Don't leave it bare. N plus n additions need at least 1 extra bit. Well, need 1 extra bit to avoid overflow. Multiplication takes 2 to the n. Use iverilog wall every session. For this, I will also say use verilator-wall on your code base, right, to get, I'll say, more accurate linting warnings. If you don't have a width written down, it's guessing. Hardware doesn't end up guessing. It will default to something, okay? Generally 32-bit numbers. Okay, next up, we're going to talk about the 7-segment display, and it's pretty cool because we're going to put everything together. We're going to build a decoder, first real peripheral that we have. It's a good preview for our next topic, the ALU. We're going to use size literals that you saw in this video, and you're going to get some lights that are not LEDs on your board, which is pretty cool. So with that, we will see you next time.